Welcome to G Fun Facts Online. Today we are bypassing the stars, ignoring the sweep of massive glaciers, and looking straight down into the dark, wet, and often smelly mud at the bottom of the world's lakes. Beneath the placid, shimmering surfaces of these inland waters lies one of the most remarkable and closely guarded archives of our planet's history. While it is easy to look to the skies to understand the weather, some of the most profound answers about Earth's climatic past and its rapidly warming future are buried in the silent depths of lake beds. Here, in the slow, relentless accumulation of sand, silt, mud, and microscopic debris, lies a continuous, meticulously detailed diary of the Earth. Every massive flood, every devastating drought, every volcanic eruption, and every subtle shift in global temperature over millions of years has been recorded in these underwater vaults. To the untrained eye, a core sample pulled from the bottom of a lake is just a tube of wet dirt. But to a paleoclimatologist, it is a stack of ancient manuscripts waiting to be decoded. By reading the sand and the microscopic clues hidden within it, scientists can reconstruct lost worlds, track the rise and fall of ancient ecosystems, and forecast the future of our climate. This is the breathtaking science of paleolimnology, the study of the history of inland waters, and it represents a frontier of discovery that merges geology, biology, chemistry, and climatology into a single, epic narrative. To understand how a lake becomes a literal time machine, we first need to understand the architecture of the abyss. Lakes act as massive topographic bowls. They naturally catch everything that falls into them or is washed down from their surrounding watersheds. Every single year, billions of tons of sediment accumulate in the world's aquatic basins. Dust blown in from distant deserts, ash from volcanic eruptions across the globe, leaves and pollen from local forests, and the microscopic skeletons of algae that bloom and die in the water all drift down to the bottom. In ideal conditions, particularly in very deep lakes where the bottom waters are completely depleted of oxygen, a state known as being anoxic, there are no burrowing worms, no aquatic insects, and no bottom-feeding fish to disturb the sediment. The material simply falls and settles, layer by microscopic layer, century after century. In some of these pristine, undisturbed lakes, the sediments form distinct, visually striking bands known as varves. A varve is an annual layer of sediment, representing exactly one single year in the life of the lake. Much like counting the concentric rings of an ancient tree, varves can be counted to establish a precise, year-by-year chronology of the deep past. A typical varve might consist of a light-colored layer of mineral sand and silt washed into the lake during the high-energy runoff of spring snowmelt. This is immediately followed by a dark, organic-rich layer of dead algae and plant matter that slowly settle during the quiet, frozen stillness of winter. By analyzing these alternating light and dark stripes, scientists can pinpoint exact years of extreme rainfall, severe drought, or sudden cooling with astonishing, surgical precision. But even in lakes that do not form perfect varves, the steady, uninterrupted accumulation of sediment provides a continuous timeline. Extracting this timeline, however, requires complex and grueling engineering. Scientists must venture out onto frozen lakes in the dead of winter, bracing against freezing winds, or anchor large floating barges in the summer to drill deep into the lake bed. They drive hollow metal tubes hundreds of meters into the earth, pulling up long, continuous cylinders of packed sediment. These core samples are immediately sealed, refrigerated, and transported back to laboratories, where the painstaking process of deciphering the mud begins. Because we cannot travel back in time to measure the temperature or rainfall of the Pleistocene epoch with a modern thermometer or a rain gauge, scientists must rely on what are called proxies. Proxies are preserved physical, chemical, or biological characteristics of the environment that safely stand in for direct measurements. Lake sediments are arguably the most proxy-rich environments on Earth, holding a diverse alphabet of clues that, when read together, tell a comprehensive and vivid story. Let us start with the pollen record, the ghosts of ancient forests. All flowering plants and conifers produce pollen, and these microscopic grains are encased in a remarkably durable organic polymer called sporopollenin. This incredible biological coating allows pollen to survive intact in anoxic lake mud for millions of years. Because pollen grains have distinct, highly complex shapes that are entirely unique to their parent plant families, scientists can look at a single layer of sediment under a microscope and identify exactly what kinds of plants were growing around the lake at the specific time that layer formed. If a core sample from a North American lake shows a sudden, sharp transition from oak and hickory pollen to spruce and fir pollen, scientists instantly know that the regional climate experienced a dramatic cooling event, shifting from a temperate deciduous forest to a harsh, cold, boreal environment. The pollen record literally allows researchers to map the slow migration of entire biomes across continents as ice ages waxed and waned. Then, we have diatoms, the tiny glass houses of the algae world. Diatoms are single-celled algae that form intricate, microscopic shells out of silica, essentially turning them into living glass. They are incredibly sensitive to the chemical and physical conditions of the water they live in, reacting to subtle changes in temperature, pH levels, salinity, and nutrients. When diatoms die, their heavy glass houses sink directly into the sediment, creating a permanent, fragile, fossil record. By identifying which exact species of diatoms dominated the lake in a given century, scientists can deduce the exact water conditions of that era. For example, a sudden massive spike in diatoms that exclusively thrive in highly saline water strongly indicates a period of severe drought, where intense evaporation drastically concentrated the lake's salts. Moving from algae to insects, we find one of the most precise temperature proxies of all, in the disembodied jaws of non-biting midges, known to scientists as chironomids. During their larval stage, these midges live exclusively in the mud of lakes, and their tough chitinous head capsules are preserved perfectly in the sediment after they die or molt. Different species of midges have highly specific summer temperature requirements to survive. By carefully tracking the changing assemblages of midge head capsules layer by microscopic layer, scientists can reconstruct past summer temperatures with an unbelievable accuracy of within a single degree Celsius. But the mud holds more than just the physical remains of plants and insects. The sand and silt contain an invisible, atomic archive. Scientists analyze the ratios of stable isotopes, particularly oxygen and carbon, trapped in the calcium carbonate shells of tiny aquatic organisms or within the decaying organic matter itself. The ratio of OXY-GEN18 to OXY-GEN16 in lake sediments is a massively powerful indicator of the global hydrological cycle. Because water containing the lighter OXY-GEN16 isotope evaporates much more readily, periods of high evaporation, which are almost always driven by warmer, drier climates, leave the remaining lake water heavily enriched in the heavier OXY-GEN18. By extracting ancient lipids from fossilized leaf waxes preserved deep in the mud, scientists can measure hydrogen and carbon isotopes to track the exact rainfall patterns, humidity levels, and even the specific type of photosynthetic pathways used by the plants growing on the shores thousands of years ago. Woven throughout these mineral and organic layers are microscopic flecks of charcoal, serving as the chronicle of fire. These dark specks are the physical remnants of ancient wildfires, blown into the water by the wind or washed in by heavy rains following a blaze. By quantifying the exact amount of charcoal in each sediment layer, researchers can construct a high-resolution history of fire frequency and intensity. This allows us to deeply understand how wildfire regimes respond to changing temperatures and varying moisture levels, offering critical, actionable lessons for managing today's increasingly fiery world. Perhaps the most revolutionary advancement in reading lake sediments today is the extraction of sedimentary ancient DNA, or cDNA. As organisms live, bleed, excrete, and die in and around a lake, they constantly shed tiny fragments of their genetic code into the environment. These fragmented strands of DNA permanently bind to clay and mineral particles in the dark, freezing cold sediment, which shields them from total degradation. Today, utilizing powerful next-generation genetic sequencing, scientists can analyze this ancient DNA to detect the ghosts of organisms that left no physical fossils behind. From just a single teaspoon of ancient lake mud, researchers have successfully identified the genetic signatures of extinct woolly mammoths, giant ground sloths, cave bears, and even early humans that drank from the water's edge tens of thousands of years ago. This technology bridges the gap between purely environmental history and profound evolutionary biology, painting a picture of ancient food webs with an unprecedented level of detail. To truly appreciate the staggering power of these lake sediments, we must look at the specific lakes that have completely revolutionized our understanding of Earth's history, acting as the Rosetta Stones of paleoclimatology. First is Lake Elgygytgyn, a 3.6 million-year time capsule located in the brutal, frozen expanse of northeastern Siberia. Its name translates from the indigenous Yupik language as the lake that never thaws. Approximately 3.6 million years ago, a massive meteorite slammed into the Arctic tundra, blasting a smoking crater 18 kilometers wide. Over time, water slowly filled the crater, creating a remarkably deep lake. What makes Lake Elgygytgyn globally unique is that unlike most of the Arctic, this specific region of Siberia was never scoured away by the massive continental ice sheets of the Pleistocene ice ages. While advancing glaciers acted like giant bulldozers across North America and Europe, erasing all older sedimentary records, Lake Elgygytgyn sat perfectly undisturbed, quietly collecting sediment year after year, cycle after cycle, for millions of years. In 2009, an international team of scientists executed a daring, dangerous mission to drill into the lakebed from a massive ice-bound rig. They successfully extracted a continuous sediment core nearly 318 meters long. When they analyzed this monumental core, they unlocked the longest continuous record of climate change ever retrieved from the terrestrial Arctic. The core fundamentally altered our understanding of the Earth's climate system. It revealed that during superinterglacial periods roughly 1,400,000 years ago, the Arctic was vastly warmer than it is today, up to 4 to 5 degrees Celsius warmer in the summer, and was surrounded by dense, lush forests rather than barren tundra. Most alarmingly, the mud proved that these periods of extreme Arctic warming occurred under carbon dioxide levels similar to, or even lower than what human industrial activity has created today. The lake's sediment proved beyond a doubt that the Arctic climate is capable of profound, non-linear amplifying feedbacks. If the Earth could get that incredibly warm under natural forcing in the past, the implications for our modern greenhouse gas-driven future are absolutely staggering. The core also offered crucial clues to the mid-Pleistocene transition, a mysterious epoch when the Earth's ice age cycles suddenly shifted from occurring every 40,000 years to every 100,000 years. While Lake Elgygytgyn provides incredible depth of time, Lake Suigetsu in Japan provides unparalleled precision. Located in the Hokuriku region near the coast of the Sea of Japan, Lake Suigetsu is a deep, tranquil basin with no large inflowing rivers to violently disturb its bottom. Furthermore, its deep waters are completely anoxic, meaning no life exists at the bottom to churn up the mud. Because of these absolutely perfect conditions, Lake Suigetsu has laid down pristine alternating light and dark varves every single year for over 150,000 years. In 2006, scientists pulled an unbroken, 76-meter-long core from the lake. Because the surrounding Japanese landscape is heavily forested, tens of thousands of fossilized leaves, twigs, and insects blew into the lake and were trapped perfectly within specific, countable annual layers. This created a scientific holy grail. Researchers carefully counted the varves one by one under microscopes, tens of thousands of them, to establish an absolute, flawless calendar. They then extracted the organic leaves embedded within those layers and subjected them to radiocarbon dating. Radiocarbon dating is notoriously difficult to calibrate because the amount of carbon-14 in the Earth's atmosphere fluctuates over time due to solar activity and variations in the Earth's magnetic field. Before Lake Suigetsu, scientists had to rely on tree rings, which only went back about 12 to 14,000 years, or marine records, which are notoriously messy and unreliable. The Lake Suigetsu core provided a flawless, direct, year-by-year calibration for the radiocarbon clock stretching back more than 50,000 years. Because of the mud at the bottom of Lake Suigetsu, every archaeologist, paleontologist, and climate scientist in the world can now accurately date Neanderthal bones, ancient human settlements, and late Quaternary climate events. The Japanese lake sediment was formally integrated into INCAL 13, the international benchmark dataset for radiocarbon calibration, quite literally resetting the clock on human history. But we must also look to the African Rift Lakes, the absolute crucible of humanity. Though less focused on deep ice ages, The massive, ancient lakes of the East African Rift Valley, such as Lake Malawi, Lake Tanganyika, and Lake Victoria, hold another monumental chapter of the Earth's story. The sediments here stretch back millions of years and are intricately tied to the rapid evolution of our own species, Homo sapiens. By drilling deep cores into the beds of these vast tropical lakes, scientists discovered a shocking truth. Human evolution did not happen against a backdrop of stable, slowly drying savannas, as was traditionally believed. Instead, the proxies in the lake sediment, ranging from dust levels indicating severe drought to shifting pollen showing the rapid expansion and contraction of dense forests, revealed that East Africa underwent periods of violent, rapid climate oscillation. Extremely wet, deep lake periods rapidly gave way to catastrophic, landscape-altering droughts. Many evolutionary biologists and paleoanthropologists now firmly believe that this intense climatic instability, permanently recorded in the lakebed mud, was the driving evolutionary force behind human development. It was not a stable environment, but a wildly unpredictable one that forced our hominid ancestors to develop much larger brains, invent highly versatile stone tools, and continuously adapt to rapidly changing food sources. The very intellect that allows us today to drill lake cores and read the climate may have been forged by the exact climatic chaos recorded within them. All of this brings us to an incredibly important question. Why spend millions of dollars, brave freezing Siberian temperatures, and engineer massive drilling rigs just to pull mud from the bottom of a lake? Why does the temperature of a summer 3 million years ago matter to us living right now? The answer lies in the severe limitations of our own modern scientific instruments. The widespread, accurate use of thermometers, satellites, and rain gauges only dates back about 100 to 150 years. In the grand, deep scope of Earth's history, a single century is less than the blink of an eye. If we only look at the instrumental record, we are trying to understand the plot of an epic, 1,000-page novel by only reading the last sentence on the final page. Lake sediments provide the rest of the book. Today, the world is warming at an entirely unprecedented rate due to anthropogenic greenhouse gas emissions. As we desperately attempt to predict what will happen to our coastal cities, our global agriculture, and our fundamental weather patterns, we heavily rely on massively complex computer simulations known as global climate models. But how do we truly know if these digital models are accurate? We test them aggressively against the past. If a climate model is fed the atmospheric conditions of the mid-Holocene roughly 6,000 years ago, or the Eocene interglacial period 125,000 years ago, it should be able to accurately simulate the global temperatures and rainfall patterns of those eras. Scientists use the hard, physical data extracted from lake sediment proxies, the chironomid temperatures, the pollen vegetation maps, the isotopic rainfall records, to verify these computer models. If the models can accurately predict the past as it is recorded in the mud, we can confidently trust them to predict our future. Furthermore, lake sediments provide a stark, terrifying warning about the tipping points of the Earth's climate system. The varves and biological proxies constantly show that climate change does not always happen slowly or smoothly. The sediment records periods, such as the Younger Dryas event roughly 12,900 years ago, where regional temperatures completely plummeted or violently spiked by several degrees in a matter of mere decades or sometimes even single years. They show us clearly that biological ecosystems, once pushed past a certain thermal threshold, can collapse and completely transform with terrifying speed. They show us exactly how quickly wildfires can take over a drying continent and exactly how long it takes for a decimated forest to recover from a megadrought. By analyzing ancient environmental DNA alongside these traditional proxies, modern conservationists are even using lake sediments to guide current ecological restoration efforts. If we know precisely what a regional ecosystem looked like for the 10,000 years before heavy human industrialization, we have a scientifically accurate, undeniable baseline for what we should be striving to protect or restore today. To hold a core of lake sediment in your hands is to hold time itself. It is a deeply humbling reminder of the sheer age of our planet and the relentless, cyclical, and powerful forces of nature that govern it. The grains of sand, the fine silt, the glass shells of dead algae, and the invisible genetic whispers of vanished beasts, all come together to form a grand, sweeping narrative of survival, total change, and deep resilience. Every single lake is a quiet, patient observer, keeping a meticulous diary of the sky above and the land around it. As we face a highly uncertain climatic future, one of our greatest hopes for survival lies in our ability to decipher these aquatic archives. By looking down into the dark, anoxic depths and painstakingly reading the stories written in the sand, we are granted the extraordinary ability to look forward, forewarned and forearmed, into the centuries to come. Thank you for listening to Fun Facts Online.